Good evening, students. Let's begin today's session.
Good evening, sir.
Good evening. So we are going to discuss some questions and doubts related to rotational mechanics and try and wind up this chapter today. So do you have any doubts from H.C. Verma in rotational mechanics? H.C.
Yes.
Verma on the module.
Yes.
You can just send me the question numbers. So let's start from with the doubts from H.C. Verma. Just if you can send me the question numbers on the text message, that would be enough. Okay, so we'll start with the 16th question. Let's go through it, everyone. Okay, so surface density, that is mass per unit area of a disk, is variable. And we have to find the moment of inertia about the axis which is perpendicular to its plane and through its center. Okay, Jay, I got your message also. I'll discuss that question also. So let's start with this one. So we have, say, a disk like this. So this is the center of the disk. We're talking about an axis that is passing through the center. Disk is rotating about this, but it has a variable surface distribution of mass. So on the surface, if we consider a point which is at a distance r from the center radially, the surface density, that is, you can write it as sigma, that is surface mass density, is A plus Br, where sigma is mass per unit area and A and B are constants. R is distance from the center. So we want to find this moment of inertia, and the radius of the disk itself, that is E. So what we'll do is we'll slice this into rings, just like we've done the derivation for moment of inertia of a thin uniform disk. We'll do it in the same way, but only difference is it will not be uniform. So a sigma will not be a uniform quantity, a sigma will be variable. So if you now slice, so this is the top view of that disk. So if we slice a thin ring of radius r, small r, and thickness, differential thickness dr. So this ring's moment of inertia about this axis, this will be a thin ring of mass sigma into area, but its radius is r, thickness is dr. So its area will be circumference into thickness. So this dm will become, now we use this value of sigma, so it is this variable into 2 pi r dr. Okay. Now this thin ring's moment of inertia about the center of mass axis is its mass into radius square, because we know that moment of inertia of a ring of mass m and radius r is mr square. We have seen this before as a standard formula. So we'll use that. So that is becoming how much? It is becoming this one. E plus br into 2 pi r dr into r square. So this is the moment of inertia of that thin ring. So now the moment of inertia of the whole disk will become the integrated sum of moment of inertia of all rings, okay, for which the radius is ranging from 0 to small a. Okay, so you have to put that as the limits. So just note down this much and try to work out the integration yourself once. I'll put up the final answer also. So this is the 16th question. After this, we'll be doing, I think, question number 26 and then 37. So if you're already familiar with this question, then you can go through these two other questions, 26 and 37. We'll discuss these. Yes, Bhargav, do you have any doubt in the question?
No, sir. I was asking like you are not writing something, then I was thinking that
Yeah,
it
you.
shows about.
I asked you to complete the integration and work out the answer yourself. I'll put it up in a minute.
Sir,
Yes.
sir, that dA equal to 2 pi r dr, how that happened?
The ring's circumference is 2 pi r and thickness is dr. So area is circumference into thickness.
Okay.
So have you worked out the answer, people, to this question now? So if you just substitute this here and integrate, so E plus BR into 2 pi, this term will become R cube from 0 to A. Okay, so this will become 2 pi comes outside. Then capital A is multiplied with R cube, so it becomes after integration. And capital B is multiplied by R to the power 4. So after integration, it becomes like this. And the limits are from 0 to A. So moment of inertia of the disk becomes 2 pi A to the power 4, we can take common. And we are left with capital A by 4 plus B into small a by 5. This kind of term we get. Okay, so it's very similar in method to the derivation of moment of inertia of a uniform thin disk, but only difference is now in this the sigma is non-uniform, the surface mass density.
Yes, sir. Understood.
All right, now let's move on to question number, what was it now? 26. Okay. So it's just a basically a monster calculation type of question. Anything else? Okay. So rotational kinetic energy of the Earth is continuously decreasing. Angular speed reduces by so many radians per day in 100 years. Find the average torque. Okay. So average torque will be equal to average rate of change of angular momentum. So it will be equal to moment of inertia into change in angular velocity over change in time. The moment of inertia of the Earth is not changing, but angular velocity is changing. So the average torque will be, now we'll treat the Earth like a solid sphere. Okay. Where me is the mass of the Earth. Re is the radius of the Earth. Into delta omega by delta t. Now this delta omega by delta t, this term, delta omega is a change of
Alpha.
0.0016 radians per day. So if you convert that to SI unit, it is 0.0016 into 1 by 24 into 1 by 60 into 1 by 60. These many radians per second. Okay. And in time, delta t equal to 100 years. So that is 365 into 24 into 60 into 60 seconds. So that will come out to be your torque. So the average torque will be 2 by 5 into mass of the Earth in SI units. It's so many kgs. The radius of the Earth 6,400 kilometers. So I'll convert that to meters into delta omega by delta t, which will be this. Okay. So this, whatever answer we get finally, this will be in Newton meters because it's an SI unit. So Harsh, hope both the questions are clear, the method.
Yes, sir. Clear.
Now next question I have on the list is question number 36. But if anybody has a doubt in anything before that, please let me know. There are some slightly complicated questions like, for example, question 27, if you have not tried it. Then even question 34. Anyhow, so I'll go with the,
Sir, can
Yeah.
we use torque equals to I into angular acceleration?
but see, here we are talking about average torque, not instantaneous torque. So when we take angular acceleration also, that will be the average angular acceleration. So average angular acceleration is that only, na? Instantaneous angular acceleration is d omega by dt, but that is not known to us. But instead we have to find out the average angular acceleration, which is delta omega by delta t, because we're talking about average torque. So that is
Yes.
delta L by delta t. So that is I into average angular acceleration. Okay, hope the point is clear.
Yes, sir.
Okay. And
Sir,
you can see
can you
that
explain 34?
34th. Okay, we'll go through 34th next.
Sir, so if average torque is asked, then we will use this only formula. Yeah.
Yes. Okay, so let's move on to question 34 next. This is kind of a heavy rotating pulley with the thread bound around it tightly. And then this is a lighter pulley, which is almost massless, according to the question. Both the pulleys are, their axles are secured to the ceiling like this over here. Now there is some thread that is wound around this second pulley, and that thread is going around the first pulley like this, and coming out from this side, and it vertically suspends the block. So the block's mass is given to us, let's say capital M, it's 2 kilograms. And this pulley, its radius is given to us as 10 centimeters. And its moment of inertia is given to us as 0.2 kg meter square. So SI unit, this is 0.1 meters like this. Okay. Whereas this is a light pulley. So because this is a light pulley, the tension on both sides of this will be the same. Because its moment of inertia is 0. Okay, so it doesn't matter whether it's rotating or not. So this tension will create angular acceleration here, and this one's weight will create linear acceleration here. So the free body diagram of the block will show us that mg minus t is equal to mass into acceleration. This is for the block. And now see, the thing is that it doesn't matter that the thread is coming out of this at an angle. I mean, it's not horizontal, because where the thread is coming out, it's still going to be tangential only. It's not going to be at some angle to the radius. It's going to be at 90 degrees only. So even if this is quite bent, it doesn't matter, okay, because the thread is still coming out tangentially. So this angle is 90, okay, and the tension is acting like this at this point. So the moment arm of the tension is the radius. Okay, so the torque that this is creating. So
So what is the meaning of light pulley? It will not rotate.
Which one?
Light pulley.
It doesn't matter whether it rotates or not. Its moment of inertia is zero. Na? So even if it's rotating, the term I alpha is zero for it, na? Because I is zero. So tension is same on both the sides.
Okay, sir.
Okay. So for this pulley, this equation becomes tension into its radius is equal to I alpha. And of course, there's no slipping at the point of contact of the thread. That's given to us in the question. Okay. So this is the block's free body diagram. This is the pulley's pulley P. Let's say this one is the pulley P. And A is equal to R alpha, because here the thread is coming out with an acceleration A, which will be related to this angular acceleration alpha of this. And that linear acceleration of the thread is same everywhere. That is the acceleration of the block.
That is constraint relation.
Sorry,
Sir, that is constraint relation.
that is a constraint. Constraint for no slipping. Okay. Now you have to just substitute these. I mean, you have to just solve the system of three equations. Okay. So try to work this out and check the answer. Then we'll discuss 37. 37 is also a very good problem.
27 done.
Okay, people. So hope you finished with this question. So you will get the acceleration as how much? G upon m plus I by r square. Sorry, mg upon m plus I by r square, right? And that will come out to be 2 upon 2 plus how much is I by r square. So it will come out to be 20, is it?
Yes.
So it will come out to be g by 11, the linear acceleration. Okay, so that's 34. Now 37. It's very similar approach, but there is like one thing which is missing in the question, which is the information about moment of inertia, but then it's given as a disk. So we have to make use of that information. Or is the other way around? Moment of inertia is given, mass is missing. So in terms of that. So G's value is taken as 9.8 in this question. So that's how it's coming out to be that particular answer. Right, so let's move on to 37th question. There's like kind of a small massless pulley over here. But then the thread so this is going around a heavy disc kind of thing. So this is the basic arrangement that we have here. So this this pulley is given to us that the moment of inertia of it is again 0.2 kg meter square. And its radius is 20 centimeters or 0.2 meters. Mass of this block is 1 kg and this is a smooth surface. So what we'll observe is the weight of this pulley. Obviously it has weight because otherwise it would not have moment of inertia. Without mass, an object cannot have moment of inertia. So let's say its mass is m0, if we don't know. So the weight is pulling it down. So that causes this to have a tendency to slip because of the tension. But also because the thread cannot slip on the surface. As this is going down, it's also rotating like this. Its center of mass is going down, and at the same time, about the center of mass, there is rotation happening. And this is going with some acceleration E prime, let's say. Okay. So first of all, there's a constraint relation over here. Thread length conservation wise, you can see that if this pulley comes down through a distance of
M naught G equal to T1 plus T2.
yeah, if this comes down through a distance of x, it will pull 2x amount of thread now. So this will have to move by distance of 2x. Okay. So therefore, my acceleration A prime will be equal to 2a. That's my thread length conservation. Plus the thread is not slipping on this, so A is equal to R alpha. That's my second for no slipping of the thread. So there are two constraint relations. Okay. Then weight minus the sum of the two tensions is equal to mass into acceleration for the pulley. So this is the pulley's translation. That is net force is equal to mass into acceleration equation. And also about the center of the pulley, you can see that the net torque, which is of anti-clockwise sense, is creating an angular acceleration alpha, which is anti-clockwise. So this is the pulley's rotation or rotational equation, that net torque is equal to I alpha. Okay. And finally, for the block, we have the equation that T1 is equal to small m into A prime for the block. Okay. So we have A prime, A alpha, T1 and T2, 5 variables, and we have 5 equations. Now it's a matter of systematically substituting this, and also we need to find this mass. So you can see moment of inertia of the pulley, we'll treat it like a disk. Is this much? So mass of that pulley will become 2 times I divided by R square. So mass of that pulley is 2 times 0.2 divided by 0.04. So it's 10 kg. The mass of that pulley should be taken as 10 kg. Now just work out the solution of the equations for the rest of the variables also. We'll discuss in a bit. Okay, so people, hope you've understood these equations.
Yes.
Let's finish the solving part. So what we can do here is T2 minus T1 into R. On the other side, we can take it alpha as E by R, and will just therefore give us that T2 minus T1 is equal to this. Okay, then we have the equation that so this is my equation 4 in a modified manner. Then I have m naught g minus T1 minus T2 is equal to m naught a. This is my third equation, and in this equation a prime is equal to 2a. So this equation will become that T1 is equal to m into 2a. That is the fifth equation. So now basically if we add equation 3 plus 4, we'll get this equation that m naught g minus 2t1 is equal to m naught plus I by r square into a. And then in this equation we substitute this, t1 is this. So we'll get m naught g minus 2 times this, so it will become 4ma is equal to m naught plus I by r square into e. So finally from this we get the acceleration as m naught upon m naught plus 4m plus I by r square into g. And we can substitute all this now. So m naught was 10 kg, so that means I by r square is equal to 5 kg actually. So 10 upon 10 plus 4 plus 5, because I think small m was 1 kg, right? G. So this is the downward acceleration of the pulley. Okay, this will come out to be 10 g by 19 is the downward acceleration of the pulley, and the horizontal acceleration of the block will be 2a. So it will be 20 by 19 g, like this for the block. This should be the answer. So acceleration of the block we have to find out. So that is like almost equal to g, slightly greater than g in fact. If you take g as 9.8, you will get 20 by 19 g as 10. Okay, so that is this question, people. So hope this is clear.
Yes.
Okay. Now, students, unfortunately, because of something urgent that has come up, I have to conclude today's class here because I have some urgent work that has suddenly come up. I have to go out. We will continue with this tomorrow. I think we have a lecture tomorrow afternoon, right?
Yes.
sir.
Okay. So tomorrow afternoon we will continue with this. In the meantime, just for the rest of the time today, it's about half an hour to 1 hour more for the lecture. You just work out questions from HC Verma, okay, particularly the rolling questions towards the end, so that tomorrow we can discuss the doubts of that and conclude rotational mechanics. Okay, people.
Okay, sir.
Okay. So thank you. That's it for today, people.
Thank you, sir. Bye.
Thank you,
Okay, bye.
Shabash.
Okay, bye, people.
Thank you, sir. Bye, sir.